Hello there. In this video we're going to go through a MATLAB example on how to numerically solve first order differential equations of any form using a finite difference approximation. So if you want to work along, open up a blank MATLAB source code and let's get started. Alright, so let's begin by cleaning up the workspace before we start writing any code. So just in case we have any things in our command window, that's going to be able to clear via the CLC command. And also if we have any open figures, then we're going to close all of them, unless you want to have them on the screen. So that's going to clear the command window, and it's also going to close all the possible figures. So the goal of this project is to solve equations of the form. So what we're going to do is solve y prime of t is equal to f of ty. And this f is going to be pretty much arbitrary, and you can make this function pretty much whatever you want. So it can contain t, the unknown function y, and any combination thereof. And we're also going to require an initial condition. So we're going to require that we know y at some initial point, and we're going to solve it throughout some domain thereafter from that initial point. So let's begin by defining our function. So it's going to be a function of two variables, t and y. Let's make this a little bit fun. Usually you want to choose a function that you can't solve by separable methods or a Bernoulli type equation or direct integration. So I'm going to do sine of t divided by t plus y plus 1, and we're going to add some exponential term, e to the minus t squared. So dot caret key squared. And remember, we use these dot operations, dot division, and dot exponentiation, just in case we want to vectorize the inputs of this function f. So t could be a vector, y could be a vector, and it will do component-wise division and component-wise exponentiation. Alright, so let's define our initial conditions, namely y of t0 is going to be equal to y0. So our t0, let's assume we're going to start at 0, and y0 can be pretty much anything we want, say 0.3. And for our forward difference parameters, so remember, we can approximate y prime of t using a forward difference, namely y of t plus h minus y of t all over h, multiply both sides by h, and then add y of t to both sides, so you get y of t plus h is approximately equal to y of t plus h times f. So h is supposedly going to be something really small. I'm going to make it just 0.01 for faster calculations. And we're going to solve, so we start at 0, and let's assume we want to end the domain at, say, t is equal to 20. Alright, so let's do our solution method. So what we're going to do is we're going to initialize our values, and I'm going to call my old value y old, and I'm going to initialize it at y0. And my current time value is going to initialize at t0. So we're going to plot our solution in figure, and I'm going to have that called figure 1, so I can reference that figure if I want to later. So I'm going to plot the t value, which is going to be t current, comma, my y old value, and then I'm going to plot it in a blue circle. So this is going to be my initial point. So if I run this, then I should get, when t is equal to 0, y should be equal to 0.3. So it definitely works. So that gives me my initial condition, which is of course truly true. And then we're going to march through time in time steps of size h. So for t is equal to, so we're going to start this for loop at t0 plus h. So that's one time step in the future. We're going to step in size h on each iteration, and we're going to finish at t final. So this is going to be our main for loop. So once we enter this loop, our current time is one time step plus what it was before. So this is the old value, we have h to it, and that's going to be our current time, and that's going to update on each iteration for this for loop. So our y new value is going to be the old y value. So remember, this y of t plus h is equal to y of h plus h times f. So this is going to be our old y value. This is going to be our y of t plus h value. So this, then we're going to add h times f evaluated at our current position times our old y position. Actually, this should be t current minus h, because this is the function evaluated at f of ty, not f of t plus hy. So this is the t plus h term, which is the current time that we're approximating this. So our new solution value is going to be located at t current comma y new. And we're using the old value t current minus hy old to help guide our solutions. So then we're going to plot t current comma y new comma, and we're going to make that a blue circle to keep it in the same value. Now we're going to hold on all of the values. So we're going to put it before because we want to hold on that value, because if we just put plot, this is going to delete all of the old points. So let's see. And we want to sort of animate that through time. So we're going to include a draw now command that's going to sort of simulate an animation style thing. For the domain of our graph, so it doesn't keep on looking weird, we're going to set some x limits on the boundary. So we're going to start at t0 minus h so we can see the first initial condition. And we're going to continue onwards to t final plus h so we can see the last point on our window and not on the boundary. And then once we're done, then we're going to reset our values, so y old is going to be equal to y new. Once we finish all of that, our final solution, title, this is going to be our differential equation solution. Alright, so let's give this a go and see what kind of thing comes up. Alright, so there's our initial condition down there. So this is going to come up. So remember, this is a sinusoid because it's like a sine t over t, so we're integrating that. So one thing we do know about this solution is that as t goes to infinity, sine t over t, its integral will converge to approximately pi over 2. So as t goes to infinity, this goes to 0, so this exponential term is going to disappear in terms of its integral as well. Because this is a Gaussian, so we know that the integral of a Gaussian should converge to some number as well. So this solution, as t goes to infinity, should converge to some y value. So this value should sinusoidally converge to that. So we're marching through our time thing at step size h, and we're almost to t is equal to 20. And once it goes to 20, then you'll see a command window then with the little cursors, which means that the function has ended. Also, once this for loop ends, then the title differential equation solution should pop up. Let's also include a grid as well. So I'm going to type grid on, and then we should be able to see our function solution. So there's our grid. So this is our differential equation solution for this particular function. You can replace anything here as long as you're not dividing by 0, because if you divide by 0, that's going to give you not a number, or a nan, if you're familiar with the MATLAB syntax. So as long as at the initial condition this value is not undefined, or you're not dividing by 0 anywhere on the solution boundaries, then everything should be well behaved. But this is pretty much how you can solve first order differential equations in MATLAB using a finite difference approximation, which is pretty much just this line here, and of course everything before it is pretty much the setup of that process. Hope you enjoyed.